This demo is about an overview of the directory structure of the ROM source code. Once you log in on the cluster and open a terminal window, in your home directory you'll find a whole bunch of these directories, and we're going to go now in the ROM's source directory. Okay, if I do an L return, I can see all the directories and files in this source code directory. First of all, there are various versions of ROMs that are available. This particular one on which we are practicing is versions 3.0, and the concepts and ideas that we'll learn about the directory structure and compilation and so forth that apply to this version are probably similar to the other versions, so this should be clear enough. Now, to simplify the discussion of this directory structure, I've created a README file which we're going to open now. All these subdirectories in the source code can be divided into four main components or sections. The first one is the Fortran code itself, which is all source Fortran codes. The second section are the directories containing the files that are used to configure the ROM's application. The third section contains subdirectories with files that are used for compiling ROMs, most likely things that you don't really have to touch on a daily basis. And then there's some other directories that contain stuff that you really don't care about. So let's talk about the Fortran code section. So here you can see that there's a whole bunch of directories. First, in order to understand this first group of directory, it is important to realize that ROMs is not just a simple ocean model, but it's actually a combination of many different types of ocean models. In particular, you have the canonical, if you like, nonlinear forward model, which is what everybody would say, oh, you have an ocean model for a simulation of the ocean, and that's okay. But sometimes you may want to do different type of ocean modeling applications. For example, you may want to run a model that only evolves perturbations, linear perturbations, and in that case you would, instead of running the nonlinear model, you could run the tangent linear model. Other times you may actually want to run not just a linear perturbation but just a fully linearized model, which is slightly different, and this is contained in this directory here called the representer model. Or, for example, you may want to do some inverse modeling and use the adjoint model, which is used to compute sensitivity and inverse calculation. Or alternatively, you may want to combine more of these models to produce other types of drivers that could be used, for example, for data simulation, and so on. Now, the CICE directory contains a source file for the CICE submodel. And then there's a directory called drivers, which contains the main Fortran program that calls the main Fortran programs, and there's one for each of these submodels. For example, there's one for the nonlinear model and one for the adjoint model and so forth. And the idea is the driver just calls a whole bunch of subroutines that are contained in these directories over here. Okay. So that's this first group, and keep in mind that if you list the drivers directory, you'll find that there's drivers for a whole bunch of things other than just the forward nonlinear model or the adjoint model. But as I said, there's also drivers that use a combination of these models to do particular ocean modeling applications, which go beyond the simple forward modeling. There's two additional source code directory. One is called modules, and this contains the definition of all variables and parameters, and that's where you will find the definition, for example, of your of the variables such as the state variables, like the velocity, the temperature, the salinity, and other variables that are used like the forcing and so forth. This is also the place where you configure all the parameters, for example, the number of grid points of your model and so forth. Now there's then a utility directory that contains Fortran code that is used for, if you like, tools like the I/O, which is the input-output, how to write and read input files or output files, and in particular ROMs uses the netcdf interface, which you can look it up on the web as netcdf. And so it contains all subroutines to read and write those files, as well as other stuff, the other tools, if you like, or subroutines that are not strictly speaking part of the physical core of the model. Okay, so this is the Fortran code, and typically you wouldn't change any of this Fortran code when you want to configure your application, because you can do so by using files that are in this group of directories, and that in fact is the core of what you need to understand. Let's start with the first directory called application. This is a directory that is not part of the standard distribution of ROMs, but is one that I've created in where I store all the files that contain the examples that we will deal with during this training. So it's some kind of a simplified version of how you can configure ROMs without touching anything else. And so we'll talk about that directory when we compile the model. But so that's what it is about. Now the include directory fundamentally contains one of the most important files of ROMs, which is the cppdefs.h. The cppdefs.h file is a file that contains certain instructions about how to pre-process all the source code in order to only retain the part of the source code that is useful for the type of application that you're doing. In a typical example, as I'll show you in just a second, is that ROMs has the ability to solve for the advection terms of the equation using different types of advection scheme. So you can pick what advection scheme you want to use for your particular application by putting some instructions in the cppdefs file, some directives in this file. And I'll show you how this works in just a second. So this is very important because through this file, basically you configure any flavor of Ocean model that you want. You can enable, for example, the nonlinear model or the adjoint model. You can run the nonlinear model with or without, for example, the Coriolis parameter, and so forth, and so on. There's then one other directory called external, and this contains templates of .in file, which are input files that are used to define the so-called runtime parameters. These are things that are not hardwired in the model and not when you compile the model, but these are just parameters that you give the model every time you call the executable. And these parameters are things like the number of time steps that you want to run the model for, or the name of the output or input files. And that's because you may want to use the executable to run different types of cases, and you don't want to recompile the model every time. And so you use these .in files to configure things. And so this directory contains a whole bunch of examples or templates that you can use and customize for your own application. Okay, so the last section that I'm going to talk about is the compiling section. And here you find 4 directories. The first bin directory contains programs used for compiling ROMs. The second directory, compilers, has templates of how to compile ROMs using different Fortran compilers. For example, if you are in a different cluster, you may want to use the Intel Fortran compiler or maybe the Portland Group compiler. And so each of these compilers has specific directives and options that are very peculiar to the compiler. And so here's an example of typical options that would work with this compiler and ROMs, the source code. There's also a directory called lib, which contains external library used by the model. And these external libraries could be things like linear algebra libraries that are called and so forth, like the RPAC library, like the BLAS library, or other sort of things. Then there's one file with a make file, and this contains instruction on how to compile the code. In fact, typically you just the compilation of the source code uses the make file, which is a typical thing in Unix, and we'll see how this works. So the next thing that I want to do is I'm going to talk about this cppdefs file. And before I do that, I'm going to interrupt this demo, and we'll just do this in the next section.